Hello, so this is video number 3 of section 4.2. This is going to be cool. I'll admit I had actually kind of forgotten how cool some of this gets, especially the vector space stuff when we look at other types of vector spaces other than Rn. But anyways, we're going to continue the trend of trying to generalize some of the definitions for our original sort of vector spaces that we defined and expand them to new vector spaces. So a linear transformation from a vector space V to a vector space W. And remember now, this means V and W here are not necessarily Rn and Rm. They could be any sort of vector space. It's just a map that takes each vector x in V and assigns it to some vector x in W, or some vector, t of x in W, and then satisfies the same two properties that we wanted our original linear transformations to satisfy. So that is, it can split up across sums, and we can factor out scalars. So t of u plus v is equal to t of u plus t of v, and t of c times u, where here c is a scalar, is equal to c times t of u. So I claim that in your we have actually seen in a previous math class an example of a vector space. So where have we seen this? In calculus, actually. We've seen an example of a vector space before. The vector space that is the set of polynomials of degree at most 2, we've already shown as a vector space. So remember, this contains all polynomials of the form ax squared plus bx plus c. And so these are the polynomials in P2. I want to look at an example of a linear transformation that you may have seen before. So we're going to let T map P sub 2 to P sub 1. And so here, P sub 1 is just the space containing all polynomials of degree at most 1. So that would be basically just eliminate this a term and all polynomials that are of the form bx plus c. Be defined by we're going to take any polynomial p of x in P2 and send it to its derivative p prime of x. For p of x in P2. Then it actually turns out T is a linear transformation. So really quickly, I want to look at this because I think this is cool. And sort of an interesting application of this to a completely different area of math. So we want to show that this map is a linear transformation. So sort of the 0th step in this, we want to make sure that T does in fact send polynomials of degree at most 2 to polynomials of degree at most 1. So here, if I take an arbitrary polynomial of degree at most 2, well, T should send it to its derivative, and so its derivative is 2a times x plus b. And so notice T is in fact a function from polynomials of degree at most 2 to polynomials of degree at most 1. Right, because notice here, every polynomial of degree at most 2 has a derivative whose degree is at most 1. Because notice sort of the degree of each term decreases by 1, so we're good there. Next, we want to check, well, is it true that T of P of x plus Q of x, we can factor T across sums? Well, so notice this is equal to the derivative of P of x plus Q of x. But if you remember, derivatives, the sum, if we want, the derivative of a sum of functions, it's just the sum of the derivatives. So in fact, t does factor across sums. And finally, we'll say t times d. If I take any scalar d and multiply it by this function, notice that the derivative is just t times 2a x plus d times b, which is equal to d times 2ax plus b which, if I sort of refactor this, is in fact equal to d times t of this polynomial. And so for all of these things, t satisfies all of the properties we'd want for t to be a linear transformation. So it turns out the map of sending a vector to its derivative is a linear transformation. Or sorry, sending a polynomial, which in this case we're kind of thinking of as vectors, to its derivative is a linear transformation. So that's actually just a really cool example that I think I thought I'd introduce here because it's always just so interesting to me to see how all of these areas of math can relate together in this way. So next I want to introduce two definitions which are a little more, I guess, specific to this sort of new way of talking about what a linear transformation is. But then we'll see that, in fact, we've seen examples of each of these definitions before. So let T from vector space V to vector space W be a linear transformation Now I want to introduce two definitions. So the kernel of T is the set of all vectors V in big vector space V such that T of V is equal to the 0 vector. And note again, be very careful here, and actually maybe I'll rewrite this a little more clearly, such that T of V is equal to the 0 vector in W. Because remember, we are allowing ourselves to think of W and V as any vector spaces now, right? Not just Rn or Rm. And so the 0 vector in W could look sort of, we don't know exactly what it looks like. It's just the 0 vector in W. All right. 2, the range of T is the set of all vectors W in W such that W is equal to T of X for some X in V. So the range is basically just all of the vectors in my codomain W such that this vector gets mapped to from V. So basically, it's just the set of all vectors that get mapped to by T. And so as a quick example, I claim we've already seen each of these things before in a specific context. Let's say we had a map from Rn to Rm, and let A be the m by n corresponding matrix. So if we go back to thinking about linear transformations for 1 second in the way we had been thinking about them, right? So up top here, we are thinking about them more abstractly. Here, we're going back to the types of linear transformations we'd seen before. Well, then the kernel, notice, is all of the vectors which map to the 0 vector in Rm. And in this context is just the null space of A, right? Because remember, the null space of A is all vectors that such that A times x is equal to 0. And the range of T is equal to the column space of A. Right, and that's because, again, it's all, so that, this is all vectors such that A times x is equal to 0. And this is all vectors B such that this has a solution. Right, and so remember here, this is just sending x to A times x. And so if x is in the kernel, well, then A times x is equal to 0, and that means that x is in the null space of A. And here, if B is in the range, that means there exists some A times x equal to B. And so this would just be equivalent to the column space. So in context of the linear transformations which we have looked at the most, the kernel of a linear transformation T is just the same as the null space of the corresponding matrix A. And the range of a linear transformation T is just the same as the column space of the corresponding matrix A. But I want to finish up with actually the same example we'd looked at before with polynomials. So we can look at these two ideas of kernel and range in a context that isn't Rn to Rm. So if we're working with matrices and you hear the words kernel or range, always associate kernel with the null space of the matrix, always associate range with the column space of the matrix. If we're working with a linear transformation that is not from Rn to Rm, and it gets a little more tricky. So again, we will let T map the polynomials of degree 2 to the polynomials of degree 1. And we know T is a linear transformation. And again, we're going to let T of P of x equal P prime of x for all polynomials P in our domain P2. And we want to find the kernel and the range of T. So we'll start with the kernel. So remember, the kernel is going to be all polynomials in P2 that map to the 0 vector in P1. So first things first. In P1, the 0 vector is the polynomial Q of x is equal to 0. Right? Because remember, the 0 vector should be that vector when added to any other vector gives me the same vector back. And so here, the 0 vector, or the additive identity, I think is sometimes an easier way of remembering what it should be doing, is just the 0 polynomial. So what we want, all polynomials of degree at most 2, or that is in P2, whose derivative equals 0. Well, this sentence right here tells me exactly what is in the kernel, because we know that this is just equal to all constant polynomials P of x is equal to c. Right? Because notice so remember P2 contains polynomials of degree at most 2. Remember, so that means it contains, the polynomial 3x minus 2, or just the polynomial, P of x is equal to 5. And so, here we just want all of the polynomials of degree at most 2 whose derivative is equal to 0. And again, that's just all polynomials with no x terms, right? So all of the constant polynomials. So there's the kernel. Last but not least, we want the range. And I claim that the range is actually just all of P1, right? So for the moment, let's assume Q of x is just an arbitrary polynomial in P1. Right, so notice this is just an arbitrary polynomial of degree at most 1. Well, I can do a little bit of integration. This polynomial Q of x is in P2, and Q prime of x is equal to little q of x. So that would be the kernel and the range of this map. So I just thought this was an interesting example. We probably won't be calling on our calculus knowledge a whole lot. I just, it was a really nice example of sort of being able to apply these definitions in a way that wasn't strictly matrices. So yeah, we can now sort of talk about linear transformations as they apply to vector spaces that aren't just Rm and Rn. And as you can see here, it really does get extremely interesting. I mean, this is so cool that, it's like, it always just amazes me that we can, define this one thing in linear algebra, which is seemingly so separate from calculus, and find that, we've secretly just, kind of defined what a derivative is in linear algebra terms. So anyways, that wraps up section 4.2. So remember, this is the last section of week 1. So you'll have Friday of this week off in order to take your midterm.